Hi, welcome back to NCRT class 10th chapter number 13 magnetic effects of electric current. Children, in the yesterday's class we came to know magnetic field across a circular loop. Means in the circular loop what is the pattern of a magnetic field we came to know. So dear children, with that previous knowledge, in today's class we are going to study what is the magnetic field pattern in solenoid. Means here a solenoid is a conductor, children, isn't it? Then how it will look like? A solenoid is a long coil consisting of a large number of turns wrapped closely, children, using a insulated copper wire. Understanding, children? It's a long coil consists of a many number of turns using a copper wire. Got it, children? Okay, now I will show a simple an example how the coil will be made. Imagine that, children, here I have taken one marker here, isn't it? Imagine that this is an insulator. Upon that, if we wrap, isn't it, this charger cable very closely, children, if we wound closely in the form of a circular pattern, isn't it, children? Then this is called what here? Coil. This shape is called what, children, here? Solenoid. Understanding, children? A solenoid is nothing but it's a coil, children. It's a long coil consisting of many number of turns which are closely of insulated copper wire. Got it? Now, what is the magnetic field across this solenoid we are going to study. Children, let us imagine this is what? Solenoid, and this solenoid has connected to the battery. Children, now we will understand what is the magnetic field across this solenoid, isn't it? When I switch on, that is when we plug the key, the current starts flowing inside the solenoid. So when the current starts flowing in the coil, means then ultimately what happens? There has to produce magnetic effect there, isn't it? Magnetism has to be generated over there, isn't it? So this magnetic field it has produced means what is the direction of the magnetic field we are going to learn. So children, when the current starts flowing in this coil, the magnetic fields inside the coil, this is what, children? Inside the coil, they are moving. See, imagine this one arrow line is indicating one magnetic field, it is moving parallel, and the second magnetic field line is moving parallel. Like that, inside this coil or inside the solenoid, the magnetic field lines are parallel straight lines. Inside the solenoid, the magnetic field is what, children? Parallel straight lines. Isn't it? Then how can we come to know whether they are moving in a parallel straight lines? For example, imagine that, children, this is a coil, isn't it, children? This is what? Coil which has wounded closely. Now if we take this one turn, then how it would look like this, isn't it, children? I am taking only this one part, children. One turn we have taken. Then at this loop, what is the magnetic field? Like this they will move, and another like this. Suppose if I take second one here, then here the magnetic field, and here like this, isn't it? And also what? Third and fourth also. In all the cases, the magnetic field lines is what? Concentric circles. And by the time they reach at the center, all the magnetic field lines are moving parallel, children. Understanding my point? When they reach at the center, all the these are all what, children? Magnetic fields, isn't it? Magnetic field lines are moving parallel to each other. Means we can find that inside the solenoid the magnetic field lines are parallel straight lines, and in fact children, the solenoid behaves like a bar magnet. Behaves like a bar magnet. You know children, a bar magnet consists of two sides, means north side and south side. Similarly, the solenoid also consists of two sides children. Then how can we come to know the sides, isn't it? For example, imagine this is a bar magnet. Understanding children? This is a what? Bar magnet. If I bring at one end of the solenoid, imagine that this is a north pole. This side is what? North, and this side is south. If I bring the north pole of the bar magnet towards the north pole of the solenoid, they will do repelling because both are north direction. What they will do? They will repel. So we can come to know that this end is what? North pole of a solenoid. Suppose if I bring if I bring the south pole of a bar magnet towards the other end of the solenoid, then they will do ripple. Suppose if I change here, means if I bring the north pole of the bar magnet towards the, imagine that this is a bar magnet. If I bring north means they will do attract each other children. So by this, by making so, we can conclude that the sides of the solenoid, if they are attracted towards the north pole means then it should be a what? North side. Suppose if the north pole of the bar magnet attracted towards the other end of the solenoid means we can come to know it is what? South end of the solenoid, isn't it? By doing so, we can conclude that a solenoid also consists of two sides like north pole and a south pole. Then, after learning that, here, when we take the magnetic field at any point children, at any point if we take the magnetic field means all are moving in a same direction. Means all the magnetic field lines are moving in a same direction. Magnetic field lines are moving in same direction. So this is nothing but a what children? Same means same can also be called as a uniform because all the magnetic field lines are moving in the same direction. Means they are all moving inside the coil. What? Inside the solenoid, parallel straight lines. Means across the solenoid, inside the solenoid, the magnetic field lines are uniform. For example, when we check at this point, the magnetic field line is moving towards what? North inside the solenoid. Suppose if we check this magnetic field means it is also moving towards what? North. So at any point here, anywhere if we cross check means the magnetic field line would give us it is moving towards north. Means all magnetic field lines inside the solenoid moving in the same direction, and because of that reason we will call what? The magnetic field in case of a solenoid is what? Uniform. This you had to keep it in mind children, very important, because in 1 mark or 2 mark they may ask what is why we will call the magnetic field lines in case of a solenoid is uniform. Means you have to write because all the magnetic field lines inside the solenoid moving in the same direction, parallel straight lines will find, and because of that reason what? The magnetic field lines across the solenoid, that is inside the solenoid, is what? Uniform. Because of that reason we can produce a strong magnetic field in case of what? Solenoid. Means in the solenoid we can produce more magnetic field, isn't it? Because of that reason it even have a wider applications children, because when we increase the number of turns means then the magnetic field produced will be also increases, isn't it, children? So it also have a great advantages. Now we will see what are those. The first one is, children, when we increase the number of turns, the magnetic field so produced can be increased. And similarly, because of this great advantage, even for magnetizing purpose, the solenoids are widely used. Means a strong magnetic field produced in case of a solenoid inside the solenoid can be used to magnetize a magnetic materials like soft iron, isn't it, children? In order to magnetize that, a solenoid is widely used, and especially in the preparation of electromagnets. Electromagnets. Widely the solenoids are used. You know, children, what are electromagnets? Electromagnets are nothing but these are those magnets, means can be called as in other terms temporary magnets, isn't it? And they will be producing a magnetic effect as long as when there is a flow of a current in it, isn't it, children? This coil is showing magnetism property only when the current is passing through it, isn't it? So in case of the electromagnets, the magnetism can be seen across it only when this current is on, means when the switch is on, isn't it? When the switch off, it is not become it is not called as a magnet, isn't it? And because of that reason, electromagnets are called as a temporary magnets. Temporary magnets. Got it, children? An idea about the temporary magnets? As long as the current is passing through those materials, it behaves like a magnet. When the switch is off, it is no longer magnetized. And because of that reason, what? The solenoid is widely used in making of a what? Electromagnet. Children, now we will discuss what are permanent magnets and electromagnets. Generally, a bar magnet is called as a permanent magnet, whereas electromagnets are temporary magnets. And when the current is switched on, they behave like an electromagnet. When the current is switched off, they are no longer becoming as a magnets. Okay, it can be called as a temporary. Means the meaning of a temporary is what? Only for a period of time. Temporary magnets. So next, we can take here we can find weak force of attraction. Weak force of attraction, whereas here strong force of attraction can be formed. Because once if we increase the magnetic field, means it will become a stronger one, isn't it? Means in case of a permanent magnets, weak force of attraction is found, and whereas in case of electromagnets, with the switch on and off, we can make what? Strong force of attraction between the coil. And here generally a permanent magnets will have that is polarities. Polarities of the permanent magnets are fixed. For example, children, this is a bar magnet. If this is what north and this is south, means we can't change these poles. Means we can't change the permanent magnets these two sides. Whereas in case of electromagnets, the polarities can be changed. Polarities can be changed by reversal of current. Means by changing the direction of the current, we can change the polarities, means directions can be changed in case of electromagnets. And the one more one is in case of a permanent magnets, only the strength is like a fixed one, we can't increase or decrease, means the strength is what, fixed, means when we take the magnet, permanent magnets, is generally its strength is what, same at all the situations. But whereas by increasing the turns of the coil, we can increase or decrease the strength of the electromagnets by increasing number of turns. We can increase the strength of the magnets, strength of the electromagnets. Isn't it, children? Because of all these wider applications we have, children, all these points, because here strength is also going to be increased, means the more amount of magnetic field can be produced, but it is what, it's the property of electromagnet, and it have advantages like in the areas of that is magnetic trains, isn't it, children? In the electric trains, widely electromagnets are used. And similarly in the hospitals, that is in case of MRI, for scanning purpose, inside if anything is there, means in order to know that the inside the body, if we want to examine, means that is electromagnets in hospitals we will use. And vice versa for children, in order to examine the cancerous tissues in our body, electromagnets are widely used in our hospitals. And also, for example, if any iron pieces, small iron pieces by accidentally felt in our eyes, means in order to remove that, at hospitals electromagnets are widely used, means these are what a few advantages of electromagnets. When you go to higher classes, you will learn more about the electromagnets, children. Only the main thing you have to remember across the advantages, children, here, that is MRI, better I'll write here, MRI, electromagnets are widely used. MRI is nothing but a, children, magnetic resonance image, isn't it, children? That is specially for scanning inside our body, the electromagnet is used. Okay, got it, children? Is it clear? So in today's class we learned that magnetic field in case of a solenoid, inside the solenoid they are moving parallelly straight lines, and in fact it behaves like a bar magnet, consists here also as a two sides, north pole and a south pole, and the magnetic field across the solenoid is what, uniform, means all are moving, all magnetic field lines inside the solenoid are moving in the same direction. Now let us have a small look into a video clip. Children, now we will study magnetic field in a solenoid. Let us study what is mean by solenoid. It is an insulated copper coil which is wound around some cylindrical cardboard or plastic tube such that the length of the coil is greater than its diameter. Then it behaves like a magnet when an electric current flows through it, and it is called solenoid. Now look at the figure of a solenoid. When an electric current is made to flow through it, then each turn of the coil behaves like a magnet. In the figure A, current is flowing into the coil in clockwise direction, so the left hand side of each turn of the coil acts as south pole, whereas
right hand side of each turn of the coil acts as north pole. In figure B, current is flowing into the coil in anti-clockwise direction. So the left hand side of each turn of the coil acts as north pole, whereas right hand side of each turn of the coil acts as south pole. Thus, this situation becomes similar to a number of small bar magnets placed end to end with their opposite poles facing each other, such that they collectively act as a bar magnet. Thus, a solenoid behaves like a bar magnet. So it is clear that if the number of turns in a solenoid increases, then the magnetic effect also increases. The magnetic field around the solenoid is similar to the magnetic field around a bar magnet.